Welcome, Calculus AB. This is lesson 5-6, definite integrals and the fundamental theorem of calculus. Let's begin. So here's what a definite integral looks like, and write this really nice. Integral from a to b of f of x dx. So what does that mean? So a and b represents the lower limit and upper limit of x. So these are of x. These are like your highest x and your lowest x. Okay. So let's say I have this function f of x. So I have an f of x function, and it kind of does this thing. So f of x, what is it? Okay, f of integration represents the area under the curve from a to b. So if a is my lower value for x, and b is my upper value for x, integrating gives me this area under the curve, just like that. So that's what it looks like. So what this is going to result in, it's always going to result in the number. So we're not going to have any plus c's when we do definite integration. We're going to get a number, like 5 is the area here, or something like that. Another thing I want to talk about while we're looking at this, I'm going to erase this, is what if the curve, the area can be positive or negative. So if my function f of x is down here instead, the area under the curve is basically the area between the function and the x-axis. So all this area will actually be negative area, but that's okay. You can have negative area. So I want to practice doing this with a calculator. And here we go. So we're doing this with a TI-89, but there's a function on the TI-83s and 84s. So I'm going to integrate this function from negative 3 to 1, x cubed minus 6x. And this is how you type it into a calculator. This is one of the 4 things you have to be able to do for the AP Calculus test. There's this function called fnint. And we'll show you how to do this in class. But you're going to go to the function fnint. In a 89, there's another way of doing this, but I'm going to go doing this way. We go nint. It's called nint in this case. It might be fnint in the 89s. Numerical integration. So I'm going to type in the equation x cubed minus 6x. And you go comma your variable x, comma your lower limit, comma upper limit. And I plug that in, and my area is 4. I want to show you what that looks like as a graph too. So I'm going to type this in as a graph, x cubed minus 6x. We're going to look at that graph. I'm going to change my window size, so zoom standard. So we're going from negative 3, which is over here, to positive 1. So it's the area under that curve. So what's kind of neat is some of this is negative area and some of it's positive. I want to actually show you what this looks like. We can integrate, and we say lower limit's negative 3, upper limit's 1. We're actually going to shade in all the area that we're integrating. So this area is negative, this area is positive, and this area is negative. When you add all 3 areas up, it adds up to 4. All right? Kind of cool. All right. Moving on. So I want to practice setting up this integration here. So let's say I give you this picture here. And this is a function 2x cubed squared minus 3x plus 2. I want to set up the definite integral. So you're integrating, you have to figure out what your function is. In the case, it's 2x squared minus 3x plus 2. And we have to figure out our lower and upper limits. And you look at the shaded area, the lowest x value here, we're not looking at y, the lowest x values is 0. And the highest x value is 2. So there's my setup right there. 2x squared minus 3x plus 2 dx. And let's say I want to actually graph that to see what it looked like. To verify x plus 2. I'm going to graph that. And we can plug it into a calculator. And I'm actually going to integrate that again, doing the same thing I just did. Lower limit 0, upper limit 2. It'll shade it in for me. It says my area is 3.333. Awesome. All right. Now, how do you find those integrations, those area under the curve by hand? Because you don't need a calculator to do this. We can actually do it without a calculator. And we call this the fundamental theorem of calculus. So it says if f prime is a continuous function a through b, so if you have a continuous function on some interval a to b where a is your lower and b is your upper, the integral of that function is going to be the antiderivative of this, and then it's going to be the top minus the bottom. So what you're going to do is you're going to integrate that function, And then you're going to be plugging in the top value, the upper limit, and then you subtract, plugging in the bottom value. So top minus bottom. Let's see what this actually looks like as a real problem. So I'm going to go integrate this one. And let's see, I'm going to actually do this in a calculator first. So I'm going to integrate negative x plus 1. And we're going to graph that. It's a line. It's going to go from negative 2 to positive 3. So actually, let's do it on a calculator first to verify. So negative 2, positive 3, shaded in, I get 2.5. Let's verify it's actually 2.5. So following the fundamental theorem of calculus, we're going to integrate this first. When you integrate that, it's going to be negative x squared over 2 plus x. And then you don't do a plus c, you put this line, go negative 2 to 3. So you did the integration, and this says we're going to be plugging in 3 and negative 2. So you plug in the top one first. So I'm plugging in the 3, I go negative 3 squared over 2 plus 3. And then subtract, plug in the bottom. When you do the bottom, make sure you put parentheses around it so you don't lose track of negatives. So it'd be negative 2 squared over 2 plus negative 2. Okay, so keep track of your negatives here. 3 squared is 9, so that'd be negative 9 halves plus 3 minus negative 2 squared is 4, and with a 4 over 2 is 2, but with a minus, that should be minus 2, plus another negative 2. So that adds up to negative 4. But we're subtracting, so it's going to be actually plus 4. And negative 9 halves. So this adds up to 7 plus negative 9 halves. 7 is the same thing as 14, so this is going to be negative 9 halves plus 14 halves is positive 5 halves, which is 2.5, and exactly what my calculator got. Cool. All right, I can do another example, but nah, we don't need to. Save it for class. We're done.